Okay, tonight's homework is it's a diagram. So I'm using a white piece of paper, but your notebook will be the next page. So you'll open up your notebook, and on the next page, you're actually going to have this diagram. So rather than like a book reading it left and right, we're going to take the left page, and that is going to become the top. Okay, left page is the top. Now, I'm going to use a ruler just because I want to use a nice straight line, but you do not need a ruler at all. So it's a graph, so it has a left and bottom. So I'm going to leave a little space at the bottom. Okay, and most of the rest of it we're going to put in color. Okay, this is called the HR diagram. It's short for Hertzsprung-Russell. Hertzsprung was a Danish astronomer, and Russell was an American astronomer, and together they made a lot of these charts to compare stars, and they found that after taking all the stars they've seen and plotted them, comparing two characteristics, they were able to gather a lot of information. So on the left is what is called absolute magnitude. Alright, so, and you can put different scales on the side, but essentially absolute magnitude is the luminosity, or the brightness of a star. Luminosity or the brightness. Absolute magnitude. Absolute magnitude is if you take all the stars and put them the same distance away and compared them. You know, not based on how close they are, because if a star is really close, it'll appear brighter, even though it just appears that way just simply because it's close. Okay, now the bottom, we are going to put temperature. This temperature is in degrees Kelvin. So essentially you add, not quite, but 300 degrees. So just add 300 degrees to any temperature, and that's what it is. So not too much different when we're talking about thousands of degrees, and that's what we are. So all the way to the right, the cooler stars are around 3,000 degrees, the surface temperature, or cooler. About midway, 6,000, 12,000. And as you can see, we kind of skip almost like exponentially, 3, 6, 12, and then the hottest stars, 30,000. These are all degrees Kelvin. And the temperature actually correlates into a color. So hopefully today in class you learned that Roy G. Biv, okay, well, the coolest stars are red, it means the hottest stars. Red, orange, yellow, green, blue, indigo, violet. The hottest stars are violet. So in pencil, I'm just going to sketch a little bit where they found 90% of the stars to be. And that was along this line. This line they call the main sequence. Main sequence stars. 90% of stars. All right? So hopefully you have your colored pencils, and we are going to fill in the HR diagram, starting with red. These stars are very small. As we move across and get warmer, the color changes to an orange, and also they start to get larger. The warmer we get, the closer we get to 6,000, they also start to change color again. And oddly enough, when we're young kids maybe, We're making a drawing. What color do we always use for the sun? Hopefully your guess is yellow. Our sun is right about here. Right at 6,000 degrees. So I'll go ahead and label this our sun. Medium mass star, nothing special about it. But it is a main sequence star. And later you'll figure out why 90% of the stars are here. So I'm going to continue on up, finish coloring. So here we have a finished main sequence. Notice that it kind of changed a little greeny, blue, and then hottest are violet. So now we're actually going to talk about a little bit of the life cycle. All stars start out as a nebula. Now a nebula is just a cloud of gas and dust. A cloud of gas and dust doesn't really belong anywhere on this chart, but just for learning the diagram, I'm going to write it right here. Okay, so all stars begin as nebula. That's just gas and dust. Now something, an explosion of another star, a supernova, something gets this going. It's this star to create. So all this hydrogen gas squeezes down and starts to glow. Generates more heat. Once things get hot enough, once fusion starts, it can become a main sequence star. But before that, it is called a protostar. All right, so I am going to use pink as my small mass star. So all stars begin as a nebula, protostar main sequence. After that, that's where it changes. So here's my small mass star. Begins as nebula to a protostar, protostar to a main sequence. And then as the star, once it runs out of hydrogen, it will no longer produce energy and it collapses down into what is called a white dwarf. Alright, so here are my circles for white dwarf. Okay. Alright, so it's a small mass star. That's things that are smaller than the sun. Smaller than the sun is a medium mass star. For a medium mass star, I'm going to use green. Starts as nebula, becomes protostar, protostar to main sequence. But a medium mass star is large enough, once it runs out of hydrogen, it'll begin to fuse and stick together atoms of helium. So once it does that, it actually grows in size and becomes a giant. So here, medium. These are giant stars. I wrote it in red because oftentimes they're called red giants. So a giant or a red giant. They're not all red. So I'm just going to call them giants. And they are pretty large. As a giant runs out of helium and no longer can fuse any heavier elements, it will implode. The outer ring of material and gases actually gets ejected away from the center, and the center collapses down to form a white dwarf. So it doesn't go back to a main sequence, so I'm going to write dot dot dot. I'm going to recreate a planetary nebula. Alright, so here is an actual picture of a planetary nebula. Here's one more. So you can see at the very, very center, right here, there is the collapsing star, and that's what becomes a white dwarf. The outer ring of the star, all that material, just millions and millions of tons of gases and other elements are just ejected out into space. So I'm going to try to redraw that very simply. I'm going to put my little star at the center, and I'm going to throw a few colors in there. So there's my planetary nebula, and the inside, that tiny little star in there, becomes a white dwarf. And there it cools down and cools and cools and cools. So small and medium mass, they become white dwarfs after they run out of hydrogen or helium in the medium mass instance. They become white dwarfs. And for a while, it was hypothesized that eventually a star, given enough time, is going to cool down. It's not going to be bright white hot anymore. And so they said eventually there's going to be black dwarfs. But a star that is that cool, at the time they didn't have any technology to, find them. Well, actually last year they've just discovered the coolest star, temperature-wise coolest. And it is the same temperature as your body. So relatively speaking, it is extremely cool. They actually call it a brown dwarf. So all white dwarfs eventually cool and become black dwarfs. It's interesting that I used to teach that they were just theorized, but we do have evidence that they become black dwarfs. So small and medium become white dwarfs. The last stage are high mass stars. I'm going to draw this one in black pen. So starts with a nebula to a protostar to main sequence, and from a main sequence they become giants, and from red giants they actually become something even larger. And when you can't think of a great name besides giant, supergiant. So that's what they are. They're called supergiants. All right. So these range. Some of them are red. Some are more orange. And some of them are more blue. So they run out of fuel, become a supernova, explode, and they rip themselves apart. The most recorded supernovas was actually over almost 2,000 years ago in 1054 AD. The Chinese actually recorded what they called was a guest star. So it exploded so bright in the sky that it lasted for a very long time. So it lasted for about 23 days, and what's significant about it is 4 times as bright as Venus. And Venus looks like a very, very bright star. So incredibly bright. So this supernova, if they are large enough, so larger than 3 solar masses, 3 times the size of our sun, they will become a black hole. If they're smaller than that, they become a neutron star, in which it collapses upon itself, the atoms themselves. So protons and neutrons in the center, electrons on the outside. The electrons actually smash into each other and form an entire star of completely made up of neutrons, called a neutron star. So here we are, HR diagram. Tonight you actually don't have to create questions. just come to class.